Now that we have reviewed the primary materials used in residential construction, we will next discuss the typical structural systems you will encounter in residential buildings. You will learn how the materials mentioned previously are used in the structure of a building. The structure is the bones of the building and must be built first. Once the structure is in place and the building is enclosed, waterproofed, and insulated, the remainder of the building essentially consists of finishes that satisfy the aesthetic desires of the owner. The structural systems of a building are usually permanent and therefore expensive to modify, while the finishes of a building are more easily modified, depending on the owner's desires. The structural systems are responsible for transferring the load of a building down to the earth. Building loads consist of dead loads and live loads. Dead loads, also referred to as a gravity load, is essentially the load of the building itself. It consists of the weight of the materials used to construct the building, plus any permanent fixtures. Live loads are temporary loads imposed by people, furniture, or the weather, such as loads imposed by wind or snow. In any building, you can trace the distribution of structural loads from the rafters and joists to the bearing walls, down to the foundation and footings, and into the earth below, where the load is counteracted by soil or bedrock. The structural system consists of a variety of components. These include, starting from the top of the building down to the earth, roof rafters, floor joists or beams, load-bearing walls, both exterior and interior, or columns, foundation walls, footings. Before we discuss the various structural components of a building, let's first learn about two fundamental components, namely a beam and a column. You may have heard the terms beam and column used in many different contexts. However, the concept of each is very simple. A beam is a horizontal structural element, while a column is a vertical structural element. A beam may include a joist, girder, steel beam, truss, etc. A column may include a steel column, post, concrete column, etc. We will now discuss each structural component in detail. Let's begin by going over roof rafters. Roof rafters are the main structural support for a sloping roof. Rafters are made of dimensional lumber, wood, or cold-formed metal framing, and spaced 12 inches, 16 inches, or 24 inches on center. The slope of a roof is referred to as its pitch. The pitch of a roof is expressed as a ratio of inches of rise per foot of run. For example, a pitch may be labeled 412 or 612, which are the most common roof pitches. Sloping roofs are generally identified as a low-slope roof and normal-slope roof. Low-slope roofs range from 312 to 412, while normal-slope roofs are 412 and up. Let's go over the components of a sloped roof. The rafters are fashioned to a ridge beam, also referred to as a ridge board, at the top of the roof, forming the ridge of the roof. Hip, or valley rafters, are used at the diagonal intersection of planes. Jack rafters are common rafters cut off at varying lengths to meet a hip or valley rafter. The entire rafter system is supported on top plates, which form the top of the bearing wall below. The roof rafters can also be supported by Cmu walls. The idea is that any dead load, the weight of the roof itself, and live load, weight of snow or moisture, is transferred by the rafters, down to the top plate, and into the bearing walls below. The roof rafters are covered by what is called sheathing, or exterior grade plywood. The sheathing is fastened to the rafters and encloses the roof. It also enhances the stiffness of the rafter framing and provides a base for which various roofing materials can be applied. Sheathing generally consists of 5/8 inch or 3/4 inch thick exterior grade plywood. The sheathing boards should run perpendicular to the roof rafters. Next, we'll discuss the eave, soffit, and fascia. The overhanging or cantilevered lower edge of the roof rafters over the exterior wall forms what is known as an eave. The eave may extend beyond the exterior wall a few inches to a few feet. Eaves help keep rainwater off the exterior walls and prevent the ingress of water at the junction where the roof meets the wall. Eaves can also contribute to a passive solar building design, as it helps prevent sunlight from hitting the exterior wall or even windows. The underside of the roof eave is known as the soffit. The soffit is typically enclosed using exterior grade plywood or gypsum board. The plywood or gypsum board is then finished using a variety of materials, including vinyl, wood, stucco, or metal. The soffit finish may reflect the material used on the exterior wall or roof. Many soffits include vents that provide the needed airflow for the roof and attic space. The face of the eave is known as the fascia. The fascia is the broad, flat surface of the outer edge of the roof. The fascia is typically made of wood and nailed to a wooden header member. The fascia is then finished using a variety of materials, similar to those used for the soffit. The next structural component we'll discuss are floor joists. Floors in residential buildings are supported by floor joists. Floor joists are made of wood members or cold-formed metal members. Joists span between bearing walls or foundation walls. They are designed to transfer the dead and live loads of a floor to the bearing walls. The required depth of the joists varies depending on the span. The longer the span, the deeper the joist. Ultimately, the required depth should be calculated by a structural engineer. However, there is a rule of thumb that can be used. For wood joists, the depth of the joist is equal to half the span in feet plus 2 inches. For example, the joist depth required for a 20-foot span is 12 inches. 20 divided by 2 equals 10, plus 2 equals 12. Wood joists are typically 2 inches wide, 1.5 inches actual width. For example, wood joists can be 2 by 8, 2 by 10, 2 by 12, etc. Metal joists are typically 1 3/4 inch or 3 inches wide, with depths similar to wood joists. The spacing between joists varies depending on the span and load imposed on the floor. However, typical spacing includes 12 inches, 16 inches, or 24 inches on center. If smaller joists are used over a long span, a 12-inch spacing between joists may be needed. Ultimately, the floor loading, span, and spacing are used to determine the correct joist depth. Joists typically want to span the shortest distance between bearing walls to avoid having deep members. When an architect is in the process of designing a building, he or she will want to identify the location of bearing walls to allow joists to span the shortest distance of a space. If this can't be accomplished in certain parts of the building, the architect may decide to introduce a girder or an additional interior bearing wall, rather than using deeper joist members. In addition to joists, you should also be aware of another structural floor component known as a girder. Girders in residential construction are made of wood, metal, or steel. Girders are primary beams in which smaller beams or joists frame into. The important point to note is that joists are framed into girders, or in other words, a girder transfers the load of a joist. For this reason, the depth of a girder is deeper than that of a joist. They are typically supported by bearing walls or columns. Girders are used for several reasons. First, the span of a space may be too long to make the use of joists feasible. The solution is to provide a single deep girder that spans the entire space and have the joists frame into the girder. This reduces the span of the joists. Second, there may not be a bearing wall at one end of the joists. The solution is to span a girder between two columns or bearing walls and have the joists frame into the girder on one end. It is sometimes necessary to install bracing or blocking between floor joists. Bracing will stiffen the floor system, prevent joists from twisting, and increase the overall stability in the floor system. Bracing consists of wood or metal cross bracing or full-depth blocking placed between the joists at 8-foot intervals. Once the joists are built, the subflooring must be built over the joists. Subflooring is the structural material that spans across the floor joists, serving as a working platform during construction, and provides a base for the finished floor. Subflooring typically consists of sheets of 5/8 or 3/4 inch plywood, depending on the spacing of the joists. The plywood is laid perpendicular to the floor joists. Blocking is sometimes added where two pieces of plywood subflooring meet. When cold-formed metal joists are used, concrete metal deck may be used in place of plywood. Concrete metal deck is a composite flooring system that includes metal deck topped with a poured-in-place concrete. Metal decking is made of light-gauge corrugated steel. Concrete metal deck typically includes a 1.5 inch or 3 inch metal deck, topped with 3 inches of reinforced concrete. The corrugated metal deck must run perpendicular to the metal joists. When openings are provided in floors, typically for stairs, additional framing or reinforcing is needed. When wood joists are used, the two closest joists to the opening are doubled up to provide additional support. Intermediate beams, again consisting of doubled up wood members, run perpendicular to the joists to form the opening. The idea behind the doubling up of joists/beams is that the opening prevents several joists from spanning between supports. The perpendicular beams are needed to transfer the load of the unsupported joists into the adjoining joists, which in turn transfers the load to the bearing walls. The same applies to openings in metal floor joists. The joists around the opening are doubled up to create a box beam. The box beams transfer the loads of the unsupported joists to the adjacent joists. The next structural component we'll cover are bearing walls. Bearing walls are one of the most important structural components in a house. Nearly all residential buildings use bearing walls as the primary vertical structural element. Bearing walls are typically constructed of wood frame, cold-formed metal frame, or CMU. In older residential construction, it is common to see bearing walls built of solid brick construction rather than CMU. In most residential construction, the exterior walls of the building are the load-bearing walls. The purpose of the load-bearing walls are to transfer the loads of the roof rafters and floor joists down to the foundation walls. A party wall is a structural wall that is shared between two adjoining properties. You commonly see party walls in townhouses. Party walls are typically built of CMU, since CMU walls not only allow joists to be framed from both sides, but also provide a fire barrier between the two buildings. How can you identify a bearing wall? Bearing walls are continuous up and down the building. If you see the floor joists or girders framed into a wall, both exterior and or interior, that wall is most likely load-bearing. If you can't see the joists, you can make an educated guess as to which way the joists are spanning. Joists typically span the shortest distance of a room or space, as discussed previously. How are bearing walls constructed? As mentioned above, bearing walls in residential construction are typically built using wood framing, metal framing, or CMU. Wood-framed bearing walls typically include 2x6, 2x8, or 2x10 studs, placed 16 inches or 24 inches on center. A sill plate is used at the bottom of the studs, while two top plates are fastened to the top of the studs. Both the sill and top plates will be the same size as the studs. The floor joists then sit on the top of the top plates and should be aligned with the studs of the wall. The next level of the bearing wall is then built on top of the joists. Cold-formed metal framing bearing walls typically use studs with 5.5 inch, 6 inch, 8 inch, or 10 inch deep webs, with flange sizes ranging from 1 3/8 inch to 2.5 inches. Like wood framing, the studs are spaced 16 inches or 24 inches on center, and the joists should align with the studs. The metal studs are fastened to tracks at the top and bottom, U-shaped members, with the joist sitting on top of the top track. CMU bearing walls typically use 6 inch, 8 inch, or 12 inch nominal dimensions wide blocks. The CMU cells are commonly grouted, and both vertical and horizontal reinforcing may be added if the loads imposed on the CMU demand reinforcing. When floor joists or roof rafters bear on the CMU wall, a fully grouted and reinforced bond beam is used below. Since bearing walls are responsible for transferring vertical loads, the number of openings in the wall for doors and windows are typically limited. When an opening, door or window, is provided, a beam must be inserted to transfer the loads around the opening. In wood frame or cold-formed metal framing, the beam above an opening is known as a header. In wood frame construction, the header consists of two members ranging from 2x4s to 2x12s. In cold-formed metal framing, the header consists of two S members to form a box beam discussed earlier. A similar detail is used at the bottom of a window opening. The studs at either side of an opening are doubled up to help carry the additional loads. This is the same concept used in floor openings, where the joists are doubled up. When an opening is made in a CMU wall, the beam used to span the opening is known as a lintel. Lintels are made of steel angles, whose size depends on the length of the span. Next, let's discuss foundation walls, another major structural component of any residential building. Underneath all bearing walls and columns are foundation walls. The primary function of foundation walls is to transfer the loads of the bearing walls down to the footings. Foundation walls are mostly located below grade. However, it is common to see the top part of a foundation wall come a few feet above grade, especially when supporting wood construction. It is important to slope the finished grade away from the foundation to help prevent any excess water, rain or melting snow, from draining into the foundation. In addition to supporting the loads of the superstructure above, the walls must be able to withstand the horizontal loads imposed by soil, as well as water, around the foundation. How are foundation walls constructed? Foundation walls are almost always made of reinforced, cast-in-place concrete. The concrete should be at least 8 inches thick, but most walls are 12 inches thick and reinforced both vertically and horizontally with steel rebar. Taller foundation walls may be 18 inches or even 24 inches thick. At the top of the foundation wall is a pressure-treated wood sill plate, typically 2x6 or 2x8, which are secured using steel anchor bolts. The anchor bolts are cast into the foundation wall, and then the sill plate is secured. The joists of the first floor and header, or rim joists, are then fastened to the sill plate. The sill plate essentially acts as a transition piece between the foundation and the superstructure. When the superstructure is built of cold-formed metal framing, a steel clip angle is bolted to the foundation wall. The perimeter channel, joists, and web stiffeners are then fastened to the clip angle. If you see any cracks in the foundation wall, it is most likely due to settlement issues. Cracks in a foundation wall can be a serious issue, as it is usually not easy to remedy the cause and prevent additional cracking. Finally, let's discuss footings. Beneath every foundation wall are footings, which spread the load from the building across a broader area of soil. The primary function of a footing is to transfer the load of the building down to the earth. Footings are always wider than the foundation walls. They are made of cast-in-place concrete and typically measure 12 inches deep by 24 inches wide, and get keyed into the foundation wall. Footings in larger buildings may measure 24 inches deep and 36 to 48 inches wide, since larger building loads need to be distributed. The reason footings are wider than the foundation walls is because a larger surface area is needed to distribute loads into the earth below. Think of the concept of a nail. The point of the nail is extremely narrow and sharp. This way, when a hammer strikes the nail, the entire force is eventually transferred to the tip of the nail, which allows it to penetrate a wood surface. If the foundation wall is not widened at the bottom, forming the footing, it will essentially act like a nail. The entire load of the building above will ultimately find its way to the bottom of the foundation wall, which has a relatively small surface area. The result will be an unstable foundation. When discussing footings, it's important to understand the frost line. The bottom of every footing must be at or below the frost line. The frost line is the depth at which water in soil will freeze in the winter. Below the frost line, the temperature of the soil and water remains relatively stable throughout the year. Water expands when frozen and contracts when unfrozen. If the footing is built above the frost line, it will be exposed to the expansion and contraction of soil water. This expansion and contraction will create movement beneath the footings, which leads to an unstable building foundation. The result can be cracks in the foundation wall and differential settlement.